Hi everyone, I'm your host Amir Jafari, and this is a series of lectures on simple harmonic oscillator. Very important, crucial, but simple, problem in physics. You can look at this problem from the point of view of like Newtonian mechanics. Very simple. You have just one differential equation to solve, easy to solve, and you've probably done this in high school or undergrad studies. And then you move to quantum mechanics. You have the Schrodinger's equation. You solve it, get the wave function, or you can look at it from the point of view of creation and annihilation operators in quantum mechanics. So you can look at this problem or use this approximation at different levels and different problems. So it's important. It's crucial to understand simple harmonic oscillator from different angles deeply. And this is the reason that Sidney Coleman once said that the career of a young theoretical physicist starts with simple harmonic oscillator, and then working out details and adding more sophistication, so on and so forth. As you go, um, move along, you're gonna get to the realm of quantum mechanics, quantum field theory, string theory, etc. So everywhere you're gonna need this concept. So this is the reason that I wanted to have these lectures prepared in order to um, use them as a reference in other lectures in our study, for example, of quantum field theory. So we can refer to equations and different concepts here, but I'm going to keep it very simple because other people not interested in quantum field theory, not interested in string theory or other areas that we are, uh, you know, um, interested in. So I'm going to mention some details, mathematical and physical details, but overall we're going to keep it simple. Okay. So let me share my screen here and start by Newton. Okay. In this lecture, I'm going to talk about Newtonian formalism, some details that can be, added to simple harmonic oscillator to make it a more realistic assumption or in more realistic problems, in fact, how you use this approximation. And then we're going to move to Lagrangian and Hamiltonian formalisms, and then to quantum mechanics, and finally, we're going to mention something about quantum field theory. Okay, so Newton said, look, I have this definition for force, right? F equals ma. A is the acceleration. It's the second derivative of the position of any given particle with respect to time. So this is Newton's second law. You're familiar with this. And then we have this problem of simple harmonic oscillator. What is it? The simplest system that we can imagine, ideal system that you can think of, is a mass connected to a spring with constant k. The meaning of this constant is going to be clear in a moment. Here we say that, well, I push this uh, mass downward, I exert some force, and it's easy to imagine, or from experience, you see that the spring is gonna exert another force equal but opposite in direction, which is basically proportional to the displacement, okay, x, with some constant. That coefficient is the constant of spring constant. Okay, and this is basically Hooke's law. Hooke's law. Robert Hooke was a great man scientifically, but he was you know, was at the same time living the same time as Newton, and Newton didn't like him because he used to criticize works of Newton. So there is an interesting story, uh, between these two. But in any case, Robert Hooke was a great scientist at his time. But the reason that we don't know much about him, other than this law, is that he's kind of, still today living in the shadow of Newton, because Newton was a, great scientist. So bad luck. Anyway, so Newton and Hooke combination gives us a differential equation, right? This is the differential equation you get combining these laws. And of course, mathematically, this is a differential equation. A differential equation is an equation which contains derivatives of a function, the function being the position here, this position x is a function of time. This is the position of this mass here, measured from the equilibrium, for example, point where there, if you put mass equilibrium state, for example, here at this point, there's not going to be any force exerted on that mass, okay? Then, as a differential equation, which is second order, this is an ordinary differential equation of second order because you have second derivative in that. So that means that because it's second order, you need two initial conditions in order to be able to solve it. For example, physically, you would say I need the position at a given time, let's call it x0, suppose you know this, and also the velocity, which is the derivative with respect to time. So if it is given 2, you have a initial value problem mathematically. This is an initial value problem. You can solve it. Okay, it's a differential equation which can be solved. By the way, it's very common to use this notation. Omega here, of course, is the angular momentum defined this way. So now we have this differential equation in Newtonian mechanics to solve. Okay, and there are different ways to solve this equation. Again, because I'm trying to keep everything simple in these lectures, let me solve it for you using different methods. Okay, so how can you basically solve it? Well, the first way of looking at this problem, solving this problem, this equation, is that, well, think about this differential equation as a physicist. Imagine that you don't know anything about mathematics. Well, you are looking at a simple, which is kind of, it's an oscillatory system. It oscillates at some period, right? So periodic functions in mathematics, well, sine and cosine. So it's easy to guess that x would be some combination of sine and cosine with respect to time. So these are, for example, in general, this kind of functions. What's alpha? Well, if you take derivative and plug in this equation, you'll see that this alpha should be omega, basically. Okay, so from there, it's easy to see that if you have sine and cosine functions as a solution, that coefficient inside sine and cosine should be omega. It comes from here, okay? How to get A and B? Well, initial conditions. You have initial conditions here. Remember, x t equals 0 should be x0. We are assuming that it's a given, okay? So it's the meaning of initial conditions. So x0, okay, let's plug in here. When t is 0, sine vanishes, so you get b. Cosine of 0 is 1, so x0 would be 1. And let's look at v, the velocity. What can you do here? Well, let's write it like this, okay. V is dx dt. The velocity of the mass, the oscillating mass, would be a omega cosine alpha t. The derivative of sine is cosine. The coefficient goes outside. Here we get a minus sign. The derivative of cosine is minus sine function. And you're going to get this function here. Sorry, not alpha. What I'm doing here. We know that alpha should be omega already. We talked about this. Okay, so it's going to be cosine omega t, sine omega t. Okay, now at vt0 at the initial time, this is going to be a omega because cosine of 0 is 1, sine of 0 is 0, so this is going to be our v0. So from here, A is V0 over omega, and from here, B is x0. So if you have initial conditions, which you should in order to solve a differential equation, you know the solution. The solution is, well, x equals V0 over omega sine omega t plus x0 cosine omega t. This is one way of, writing the solution. Okay, sorry, this is not, okay. This is one way of writing the solution. There are other equivalent ways. Let me write this properly. So this is your solution for simple harmonic oscillator. And you see that it's written in terms of sine and cosine. But there are other ways, for example, using this identity or definition, Euler formula, which is cosine alpha plus I sine alpha. I is the complex number here. If you are familiar with complex numbers, you can use this formula to rewrite the solution as a complex function and get the real part. But if you're not familiar, it's okay. But it's obviously you can write it in, and you can combine actually sine and cosine in this formula to rewrite it again as a single sine or cosine function, so on and so forth. So there are different ways, but this is one way, and it's equivalent to other ways. And another way to solve this differential equation, which might be useful for you in other problems, is that, other than guessing, is that you can write, let me write it again here, you can use a change of variables, and physically it means that you are writing this equation, which is a differential equation for x position, in terms of the velocity of the mass, right? So v is dx over dt, right? So this, the left-hand side is basically d over dt, dx over dt. It's the second derivative, right? So it's basically dv over dt, because dx over dt is velocity. So it means that you can write down this equation as dv over dt minus omega squared x. But now you have three variables here. You have one differential equation, but you have three variables. V, velocity, t, time, x position. How to solve it? Well, there's a trick. Write this as dv dv dt, add dx here, multiply by dx, and divide by dx. What you get is dx over dt now is v, and this is dv over dx minus, and you can rearrange it to write it this way. X times omega x dx. Okay, this is what you get. This is the differential equation you should solve. But this is really, the variables are kind of separated, so it's easy to integrate. You integrate v dv minus omega squared is the constant, x dx, and from here you get v squared x squared plus some constant. That constant can be called c over 2 because it's a constant. So you can get rid of these 2's. This is what you get. Okay. So mathematically, what you need here is to write dx over dt instead of v squared, and then omega squared x squared plus c. Then this is going to give you dx. You can write it this way, right? Dx square root of minus omega, so plus minus, after taking the x plus c plus it's equal to dt t, and then integrate. And then from here you get arc sine, arc cosine functions. If you know this integral, you can look it up in tables of indefinite integrals. It's easy to see that it's given in terms of inverse functions, inverse sine or cosine. So you basically recover the solution you already had. But as a physicist, you should also notice that here what you have is basically the relation for the total energy. If you multiply this expression by m/2, mass of the particle, so you're going to get, and then by rearrangement, you're going to get m omega x squared plus cm, say 2. And this is basically the total energy of the system. This is the kinetic energy, remember. And this is the potential energy. So the potential energy of the spring, the system, is 1/2 kx squared. Okay, this should be familiar again. So this is another way to look at this problem, and it gives you the same result. Now, if you, as I said, know enough about Euler's formula and complex numbers, in general you can write xt as something like this: ai omega t plus another constant, a and a star, just constants here, minus I omega t. Omega is the angular frequency, and remember, ei omega t is cosine omega t plus I sine omega t, and I is obviously the complex number. Now, because physically the position should be a real number, so in fact, this is very common in physics. When you have a real variable, real quantity like position, you write it, it seems like, it's common to write it as a complex function, because it's a complex function. At any given time, it's going to give you a complex number, but it don't mean that we are working with, imaginary positions or complex positions. It means that implicitly we are interested in the real part of this function, which gives us the physical position, right? So, for example, here, the real part of ei omega t would be cosine omega t. So this is the imaginary part, this is the real part. And also remember that this a and a star as coefficients, as constants, are again complex numbers. So you have to take the real part of the whole expression, okay? So any complex number c is written as real part plus I imaginary part. For example, you see, say c is a complex number, you can write it as a plus ib. Now a, b, c are real numbers, but now this, sorry, not I, not c. A and b are real numbers, and c is a complex number. Okay, so the point here is that when you write the solution, because we're going to use these lectures as a reference, so when you write xt as like some constant ei omega t plus some other constant or complex conjugate out of a omega t, well, physically, this is the classical solution, and you take the real part, and it's your solution, and you get sine and cosine functions from there. But interestingly, when you treat simple harmonic oscillator quantum mechanically, it's going to turn out that what you do in quantum mechanics, very briefly, you say that x position, p, momentum, and energy, and other variables like angular momentum, etc., now they are operators. They're not numbers or vectors. So you promote position to an operator, momentum to an operator, which is basically this operator in terms of gradient operator. H bar is the Planck's constant, I is the complex number, and energy is also promoted to a operator which is time derivative basically. And then what you get for simple harmonic oscillator, this is quantum mechanics, and this is called first quantization. Okay, and it turns out that between x and p there should be some commutation relations. If you are familiar with quantum mechanics, you should know this stuff. But the point here is that then x for simple harmonic oscillator turns out to be something like this: I omega t plus e minus I omega t. So the form of the solution is almost the same, but remember that x now, the position is not Newtonian position. It's not a number. It's not a displacement, a real number. It is an operator. If you are familiar with ordinary quantum mechanics, you know that x there is an operator, and that operator turns out to be, it can be written in one formalism. We're going to talk about this, Dirac's formalism, in terms of these two operators, again, A and the dagger. And I noticed that I should put this a dagger I minus I omega t. So the point is that you see the similarity between classical, this is classical simple harmonic oscillator, and this is quantum simple harmonic oscillator. The solutions look very similar, but they are very different because in quantum mechanics we have operators. And we're going to talk about this, the meaning of these two operators. This is called creation operator, this is called annihilation operators, and they are related to creation, annihilation of photons or particles in quantum field theory. We're going to get there, but this is just a side note, okay? This is what you get in Newtonian mechanics for the position of a simple harmonic oscillator in terms of complex numbers. You have to take the real part of this function to get the real physical position. Okay, so now let me also mention something about the this approximation. The simple harmonic oscillator is basically something ideal. It's an approximation of real systems when you have an oscillation in a system, in an atom, for example, or in musical instruments. You have these oscillations. You can treat them as a bunch of simple harmonic oscillators, etc. Again, we're going to talk about this in other lectures. Condensed matter physics, very useful concept there. This is the building block of many theories in physics, in string theory, everywhere. But the point is that this is an approximation, but it's very useful, very important approximation. However, before leaving Newtonian mechanics, let me also mention that when you say my force, Newton's second law, this is the force acting on this harmonic oscillator, right? And the Hooke's law gives you this minus kx, force. This is the external force acting on the mass by spring. Suppose that you don't know anything about Hooke's law. You have some oscillator system, you know Newtonian mechanics, but you have no idea about this force exerted by this spring. So you have this relationship, then, this equation. You know Newton's second law, this is the definition of force, but you have no idea how the spring actually exerts force or pulls or pushes this mass. You don't have any formula or any idea about this force of spring here. Okay, you don't know anything about the Hooke's law. Well, you can say that, well, I have some equilibrium point, say here, x0, and I call it the zero of my coordinate system. So when the mass is at that point, the origin, x0, at 0 point, there is no force, okay? Then, when I displace the mass from that point, I feel some force, restoring force, by this spring acting on the, again, I have to write on the left-hand side so you can see it, this spring's constant. So you can see that I have this Taylor series for my force. You Taylor expand this unknown force exerted by the spring. And because in equilibrium there is no force, this should vanish. And so this is going to be something like this, right? I'm just repeating this to be extra clear. And also, empirically, you know that the restoring force, when you pull the mass, this spring pushes it. When you push the mass in one direction, this spring pulls it. So the force of this spring is against the displacement of this mass, always. So you say that, well, this constant here, I'll call it minus k. K is a positive constant now. You put a negative sign in order to take into account of this restoring, nature of this force. Plus some constant here, and maybe something like this, higher order terms. But then you say that, well, let's look at the simplest system. Let's look at a system where the displacement is not too large, so in such a way that these higher order terms are negligible because you have, higher powers of x. So if x is very small, higher powers of x would be extra small. So from here, you get the equation for simple harmonic oscillator. So you see that simple harmonic oscillator, in some sense, is an approximation. In general, your system, your spring, can have a non-ideal behavior. So the restoring force by this spring is not going to give in by the Hooke's law. The Hooke's law is a good approximation in some sense. But in general, we're going to have these other terms, higher order terms, or we can imagine them. Let's call them, I don't know, x squared, gamma, etc. One more thing. What about friction? We have air, we have friction between the, if it's on a surface, I mean here I have this simple harmonic oscillator prepared in a vertical direction, so there is no surface to have friction with, but there is air. If there is a vacuum, well, you can get rid of this, kind of friction with air. But in reality, you can have another function here, let's call it Jx and V, which might depend on the position of the particle and also the velocity of the particle. So, for example, friction in air, when you move in air at slow velocities, the friction with air, the air resistance, can be approximated by a force against the motion, which is proportional to the velocity. Okay, so it's like something like minus some constant beta v. So it's a kind of frictional force. But in general, it might depend on x, the position of your mass as well. So what we call this is a source. Here it's an external force, or a source which basically drives your simple harmonic oscillator or harmonic oscillator. Okay. So this is a more general system, which is not harmonic anymore because you have higher order terms, you have a driving force or a frictional force, a damping force. This is the general system, and the reason that I'm mentioning this is that, for example, in our treatment in canonical formalism of quantum field theory, when you look at the Klein-Gordon equation, which is the Klein-Gordon equation is the differential equation for a field, a quantum field. When you Fourier transform that field, you get something like simple harmonic oscillator motion or simple harmonic oscillator equation for the Fourier mode. And there you'll see that these higher order terms basically correspond to interactions between particles. Okay, and this J is basically acts like a source for particles. For example, in quantum electrodynamics, in a very simplified picture, because there we have spin, the polarization of photons, etc. But when we treat electromagnetism quantum mechanically, we have to have some formalism in order to, create and annihilate photons. Okay, and these photons or these new particles in other quantum fields can have interactions with each other. So those interactions are, related to these higher order terms. And also you can have sources or currents, for these particles, for these fields. And there you'll see that this J plays the role of a source. So keep this, formalism, this equation in your mind, because you're going to need this, to think about these lines when you take a course in quantum field theory, where we talk about these interactions, etc., in perturbation theory, for example. Also, last word, remember that this is not, when you talk about simple harmonic oscillator in this way, a spring, mass, etc., this is not the only, idealized system that you can have this sort of, equation for that. For example, there are other systems. For example, you can have a string, and say you have a mass, and you can rotate this mass, okay? And by rotating this mass, you're going to have some torsion in this spring. Now, this is a rotational simple harmonic oscillator, if you like. So here omega is k over m. Here omega would be something like mu over I. I is the moment of inertia, and mu is the torsion constant here, kind of, rotational spring constant. Another example would be an LC circuit. For example, you have some capacitor here, an inductor here, and this is a circuit which is called LC circuit. Okay, there you're going to have the same, equation of motion. But let me get this for you. In this particular example, if you start from here, let's say that here you have some potential E, right? Then you start and you go in this direction, it would be minus L di dt. If you are familiar with electromagnetism, this should be familiar to you, but otherwise you can ignore it. When you pass through the inductor, you're going to get a drop in potential. This is potential. I'm talking about the voltage, the potential in the circuit. And when you pass the capacitor, basically you have a drop, because capacity is defined as the charge over potential difference. So V would be Q over C, so you're going to get to the same point. Say this is point A, this is the potential at point A. So from here, what you get is L di dt equals minus Q over C. I is the current, electric current, and I is basically defined as dq over dt. Q is the electric charge. So what you get, and I can bring L over here, what you get in terms of Q would be d squared Q, and you can call this minus omega LC Q, or Q minus omega LC Q. So you see that this is simple harmonic oscillator equation of motion. So you get this, equation, this system, this behavior in many other problems and systems in physics. And Newtonian mechanics of this system is simple, although, as I mentioned, in practice, you're going to have corrections, you're going to have higher order terms, you're going to have friction or a driving force. For example, in a grandpa clock, you have some oscillatory motion, simple harmonic oscillator, but because you're losing energy due to friction, you have to have some force, some restoring force to help the clock, run. So you're going to have an external force, I call the J here, and you can keep this term and this term. So depending on the problem you have, you're going to have different terms. But if there is no damping force, friction, etc., or driving force, like a battery in a clock, etc., and it's an ideal spring and mass, then this equation would be enough for you, and this is simple harmonic oscillator. Otherwise, it's not simple harmonic oscillator. So I guess that's it. From a Newtonian point of view, this is what we need. And let's discuss the Lagrangian and Hamiltonian method in another lecture.